Hello fellow problem solvers. So today we're going to be doing a problem from the 2013 IMO, problem number 2. This is one of those problems that you just find beautiful. I mean, it's nice at the very minimum. And at the very minimum, I would invite you to try this out for a minimum of half an hour. Ideally 90 minutes to 2 hours, not more than 4.5 hours. If you'd like to go along with us, give this a go for the next 30 minutes. And now let's begin. And at the end of this, I'll also tell you a funny story about a friend of mine who was actually at this IMO. So let's begin with this problem. We have, let's understand what's happening here. We have that 4,037 points. Okay, 2013 are red, 2014 are blue. They're in a Colombian configuration. That's where the IMO was. If and only if we have that none of them are on the same line. That's basically what a Colombian configuration is. And then we put some lines. Well, okay, so we have some of these points. And a configuration of lines is good if the points in every region formed by these lines are what's it called? That every region doesn't have 2 points of the same color. Yeah. So, no, that every region doesn't have 2 points which are of different colors. That's what a good configuration is. We need to find a case such that we can always, if we have K lines, we can always make a good arrangement of a Colombian configuration. So, what is the first thing you would do with this sort of problem? For me, this is true when I did it. This is going to be true now when I'm doing it again with you. When you don't know what's happening, like 4,000, looking at 4,027 points, 2014, 2013, those are big numbers. There are lots of possibilities. It's too difficult for me to comprehend like all the possible configurations of 4,000-ish points. So forget about 4,000. Let's say, okay, let's make this n and n plus 1 and work our way up until 2013. So we're going to try to see like what happens if we have 1 red and 2 blue points. 2 red, 3 blue points, then 3 and 4. And this is what I'll invite you to do for the next 10 minutes. Of course, please read the problem. And now let me clear up the board and go through all of these cases. And now that the board has been cleared up, let's look at 1 and 2. So say we have 1 blue point and 2 red ones. Okay, so a red point here, a red point here, and a blue point just not on the line. Well, this is not a blue marker, or we'll make do. Let's see how my blue marker looks today. That's decent. Let's use the blue one. Okay, well, if we have this, I can just like draw a line here. I can make it as close as to these 2 red points, such that the blue will be cut off. So there's no issue there really. Let's look at 2, 3. I mean, K is 1 here, right? No matter what the configuration is, they're going to form a triangle, and then we can do this. Now let's look at what happens if we have 3 red points. 1, 2, 3 red. And 2 blues. So now it actually matters where the blue ones are. Say I have a blue one here and a blue one here. Okay, now these are points of a convex pentagon. And I should be able to do this in 2. In fact, I need at least 2 lines. Because why do I need 2 lines? Well, can we prove this? I think we could, because this is a convex pentagon, and we need, if the point, these lines need to cut through the lines I think need to cut through, like every red point connected by a blue point needs to have a line cut through it, otherwise they're not separated. Now this is a good way to think about in general this idea of what is necessary. Like you can give us a lower bound. Because mind you, this thing with K, you need to show 2 things. 1, that the given k we're going to find always works, no matter the configuration, but also you'll need to show that there's a configuration in which you can't do k minus 1, right? You need to show both those things. Like if the answer was say 10, you need to show that 10 always works, we can always use 10 lines. And also you need to show that there's a configuration where you can't do it with 9 lines. You can't separate them out. So this seems, okay, we have 2 lines. Now are 2 enough? I invite you to pause for 3 minutes and think about whether or not 2 lines are enough. And the answer is, well, you can see, like, looking at different cases, I can just, no matter if instead of the blue one being here, the blue one was, say, somewhere here. I mean, this would literally be the same situation, but say it was like somewhere inside, say here, so that it's not collinear. I need 2 lines, I've shown in the previous example, so I can just create like this little thing, like a tube, that collects these 2 blue points and leaves out the rest, right? So that's an idea. And now for 3 and 4, I invite you to pause for another 10 minutes and see if you have an idea, and try to solve it, the problem for 3 and 4, because right now we're getting k is equals 2 for this configuration of 2 and 3 points. And now the thing with 3 and 4, we're going to have, let's see, we're going to have 4 red points, and now we're going to have 3 blue ones. Okay, now the tube argument doesn't really work here. I mean, in this configuration, we could tube these 2, and that would give us 2 lines and another one here, and it would give us a 3rd line. But I'm curious, like, we could do it in 3. I'm not curious whether the solution is k is equal to the smaller one of these. Like, for evens, it seems like it has to be, right? For even, if the smaller one is even, it seems like we'll just be able to whoop, 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 tube them up and be done with it. Though our trouble is that the smaller one is odd, so we can't just like tube them up. So we have to figure out a different approach. So let's see, what do we have? Okay, if this one's on the outside, we could also finish up. What if they're all like inside here? We'll also need to figure out like what this inside-outside thing means. I mean, then I can actually do them with 2 lines. Let's say there was a red point inside here as well. And maybe one on this side. Maybe instead of the red point being here, it's here-ish. Maybe it's between these 2. Can I chop them off? I mean, I still should be able to just like making them these 2 very small. I can get 2 of them. And then the 3rd one, I can just get out like this. Now, what am I using here? That's the question. What am I using here for 3 when I have 3 and 4 points? What is something that is important to me? Is there some structure we can look at here? This is where I would invite you, yes, you, to pause for it. Another 5-10 minutes, see if there's any sort of formalization you can give it. Like if there's one on the sides, on the edges, so to speak, we can get 1 line and put the other ones in tubes. How would you formalize these on the edges? Really think about that. And actually try to push this problem forward, because it's a beautiful problem. I would really like you to try and solve it yourself. I've given you a lot of cool ideas here. Now, the next sort of bit is, okay, well, let's use a convex hull, let's make a thing, a n-gon, such that inside it are all the points in this configuration. So because we have 4 and 3, let's say there's 2 points inside. Now, what do we have? In which case are we done? Pause for 3 minutes, ask yourself that. And the answer is, if one of the points on the convex n-gon, on the convex hull, is blue, right? I'm saying 3 blue and 4 red. Then I can cut this one out, and then the other 2 blue, wherever they are, I can just put them in a tube, right? So with that, I will be done. Now the only question is, what if all the points in this convex and gone are in fact red, and say there's 3 points in the, like this triangle covers all the points, and then we have 4 other points inside. What do we do in this case? Now we have all of these there's a red one, a red one, a red one, and say a red one. What would we do in this situation? Well, for me, the idea is, wait a second. If I cut out these 2 red ones, I can cut them out with 1 line. Then I'm left with 2 reds and 3 blues. And if I have 2 of one and 3 of the other, I can use 2 tubes. So I can then sort of finish inductively and be done. And now here, with this in mind, is there a way to perhaps generalize this to a bigger case? How are we going to now solve the problem for our 2013 and 2014 points? What is K? And also, mind you, wait a second, now I'm getting a bit too ahead of myself. We're now only showing somewhat, we're like going towards the idea that if I have n blue points and I have n plus 1 red points, that K is equal to n, right? That's what I'm showing. That's sort of what I'm like trying to say, that I can complete them with K, but I need with n. But I need to show that there's a configuration in which I can't complete them with n minus 1. So we still need to posit this 3 at 4 and try to construct one configuration where we absolutely need at least 3 of these lines. And here's where I invite you to pause again. If you haven't come this far, pause for another 10 minutes, try to push the problem forward, maybe even 15 minutes. 20 if you have the time, please. Pause. Yes. Now, let's get back to the problem. So what do we have? We are going to try to see how to construct this such that we need K to be equal to 3 for the case 3 blue and 4 red. So now, we had this idea of a pentagon here where it was like sort of necessary. 5. Now what if we had a 7gon? How many do I have? 1, 2, 3, 4, 5, 6, and say 7. And now, if I just alternate their colors like this, then I've sort of forced myself to have how many lines? Well, every line goes through 2 segments, goes through at least 2 segments, right? And if I take a blue point, if I connect it to these 2 neighboring red points, there needs to be a line to separate this point from this one, these 2 points. There needs to be a line through this segment and a line through this segment. So that's 1. To separate this blue one from these 2 points, there needs to be a line through both of these segments. And that's another line. Separate these 2, we need another line here, and that's a 3rd line. So in essence, we need at least 3 lines in this case. And now is the time for you. Your turn. Get to 2013, figure out how you'll get to 2013, what you want to prove, and pause and try to do that for 20 minutes. If you can, you'll feel very good about yourself that you've been able to solve an IMO, problem number 2 in combinatorics. And it's a beautiful problem. And let me clear up the board now. And now that the board is cleared up, let's see, what will we do here? We would sort of try to prove the claim inductively, saying that if we have n points of one color and n plus 1 of another color, in a Colombian configuration, meaning no free arc linear, then we need at least k is equal to n lines to cut them up. And rather, on the induction side, we can just prove sufficient like that. If we have n lines, that's enough to separate them out. And the way we'd do this is we'd say, okay, let's draw the convex hull around these two n+1 points. So here's that convex hull. And now we say, one of two things is true. We're going to prove this by induction. We've proved this for n equals 1, 2, and 3. Now, for the convex hull, we say there's one of two cases. So this is the number of red points, and this is the number of blue points. Now, if n is even, we can pair up the blue points and put them into those tubes. And then we'll have every tube consists of two lines. We can always do this such that it separates out from the any 2 points, because what we'd say is take 2 points, doesn't matter which one, but they're blue, and take the red point that is closest to it. Let that be on a distance of these 2 points. Then draw a line that's parallel to the one connecting these 2 blue points, and that is of a distance d/2 from both of them. That's a way that you can prove, and it would be nice to actually prove these things. Like just by saying this, you actually proved it. If there was a red point inside, it would be of a shorter distance than d. Contradiction, right? So if n is even, we're immediately done. So for all intents and purposes, assume that n is odd. Now we're looking at n is odd case. And what happens there? Well, we say if n is odd, then n+1 is even. Now, if one of the points on a convex hull is blue, case 1, like actually case 2, subcase 1, if one of these points is blue, then we say, okay, we're going to draw one line to separate this one out from all the other points. And we can do that. We can get it as close as, we can get this line such that the distance from this point to the line is the shortest possible distance among any other points to this line, and that the other points are on this side. Something like that. That's sort of the argument. I mean, we can keep moving the line up and up and up until we reach this point then. Okay? So now with that in mind, we have this point separated. And now by induction, we have, actually not by induction, we've separated out this point with one line, and then we have n-1 blue points. Now what can we do with them? Well, we can pair them up into these tubes. And when we pair them up into tubes, because we can pair them up 2 by 2 of them, and we'll use n-1 lines. So in total, we're using k is equal to n-1 plus n plus 1 is equal to n lines. Now, if all the points on the convex hull are red, there's at least 3 points on the convex hull. So there's 2 neighboring points which are red. And we'll say we take a line that separates out these 2 points from the rest of them. And now what do we have on the other points? We have n-1 red points and n blue ones. And by the inductive hypothesis, we know that we can separate these out using k equals n-1 lines. So the other ones are going to be separated with n-1 lines, and the one other line, we're going to have k is equal to n lines is enough. And we proved this now by induction. Ta-da! And this is showing that k is less than or equal to 2013. Because we've shown if we have 2013, that is enough. Now can we show that there's a configuration where we need 2013 lines? And we say Yes, the AK regular, it's easier if you say it's a regular, or no, put them on a circle, even better. I mean, if it's a regular Engon, it's on a circle, but regular 2017 Engon, label the points A1, A2, all the way till A4027. And then we say, let's color the odd ones. I think if I color the odd, yeah, let's color the odd ones red. And now we have that we need to separate out the points A2k minus 1 and A2k with a line. For k is equal to, for k, 0, not 0, from k is equal to 1 through k is 2013. I need to separate out. So wait a second, I need to separate out A1 with A2. Oh, wait a second, I need to separate out these two. And A2k and A2k plus 1. For k is equal to 1 through 2013. Now, that means that there needs to be a, what's it called? A line going through all of these, what's it called? How do we put this? There isn't, if a line goes through one of these segments, one of these 4026 segments, then it's going through the circle as well. Then it's going through the arc A. If it goes through the line segment, AI plus 1, then it's going through the arc, the shorter arc AI plus 1 on the circle, and given every line can go through most 2 points on a circle. Is that so? I think, yeah, that's self-evident, but I'm thinking, how do I prove that? Now, we have this, every line goes for at least, what's it called, one of these. So every line can go for at most 2 segments of these 4026. So we are going to need at least 4026 over 2 lines to make them separate, to separate out these points, which is equal to 2013. So k 2013, k needs to be greater than or equal to 2013, less than or equal to 2013, and therefore k is equal to 2013 is our answer. And this finishes up the problem. Now, I absolutely love this problem. It's one of my favorite problems from the IMO. I wish I had it. Now for the funny story. So a friend of mine from our team went to the IMO, and he got sick during the first day, and he needed to finish early. He needed to finish both days early. And what happened was, either he misread or it was badly or the first problem was badly translated. So he skipped over the first problem at the IMO, worked on the second problem, worked on it for like 90 minutes or so, and then submitted his paper. And he worked on 90 minutes both days, and he was a point or 2 away from bronze medal. But he solved the second problem. And it just goes to show, like, when you're going to these competitions, you should also be aware that you don't get food poisoning or something like that, because that can derail you. Like, imagine that. In 1/3 of the time, he was 2 points away from bronze. That's why we call him the machine, or the boss. And this finishes up the story and this beautiful little problem. And as always, thanks for problem solving.